Yeah, I want to talk to you all about some research I've been doing with Paul Estrada, Jeff Cuzzy, and Thomas Hartlett. And it was work that was instigated at the by after the conference on the accretion first billion years at LPI. So I like to also give a shout out to Alan Tremaine for the for helping to instigate this line of thought here that I'm going to share with you all. Okay, so you know, this is a crowd of experts, so I don't need to get into much depth about the motivating factors for what I'm going to talk about. I'm going to be thinking a lot about the inner solar system, and one of the things that of recent interest that is a result of a lot of the work that's been done by people like, for instance, like Justin Simon, is analyzing some of the meteorite data, and there's been some very interesting breakthroughs. And essentially the meteoritic evidence, as we all pretty much have come to agree that planetesimal growth in the inner solar system was probably done between 1/2 and 2 million years. And this latest meteorite, this NW Northwest Africa 5717, it's very interesting because it actually suggests that there's been, during those first million or so years, there's a lot of mixing going on in the inner solar system. And even after Jupiter appears, even after Jupiter forms, work done by Cryer, for instance, it suggested that the regions that were separated by Jupiter were also fairly well mixed, with the occasional kicking over of material across the gap. But it's basically this sort of separated region that's undergoing some effective mixing. So, and what's interesting about this chondrite, this chondrule, is that these chondrites have chemically and lithologically distinct inclusions, which again suggested this widespread mixing. And just to kind of keep this in mind, if you look to you see sort of a lighter lithology and a darker lithology, and you'll see grains that are on the order of, you know, a few millimeters, and they form on they form centimeter scale aggregates. So, you know, in all of our thinking over on this side of the world, we're always thinking about how to address, you know, this type of data. And so, of course, this is the motivating factor. So this is nothing new to the crowd out there. There are these, this picture of the growth of particles from the micron size up to, say, the 100-kilometer scale, planetesimal scale that we're all interested in. And we know that there are several particles will grow until, through sticking, until they reach these various scales that prohibit growth, what we're called barriers to growth. There's the bouncing and the fragmentation and the drift and several others that I haven't listed. But one of the big interests, of course, is to leap over this barrier, somehow going from, say, meters, centimeters to meters scales up to 100-kilometer scales. So that's what I call making our way to the promised land. And there are several mechanisms that can do this. Pebble accretion, turbulent concentration, streaming instability, vortices, and so on. It's not even a full list that I have down here. Some pebble accretion may actually sit perhaps as a mechanism that sits outside of this list, only because it probably works, and it likely is working once you actually get a core to go. And once you have a core, then pebble accretion is the mechanism around. So I'm more interested in is how we even get to these cores to start with. Okay, so as I mentioned here, there's ways to the promised land. There's the idea of pressure bumps and the Rossby wave instability, steady vortices, affected at collecting particles. I don't want to talk about that here. It's been looked at quite extensively over the last 10 years. The other mechanism is what's called the turbulent concentration, and this is an idea that's borrowed from ideas in atmospheric turbulence, where if you drop a bunch of particles into a turbulent medium, and let's suppose it's like 3D isotropic turbulence and has a Kolmogorov spectrum, what you will find is that you will get preferential particle clumping if the Stokes number of the particle matches this. Let me rephrase that. If there will be a scale at which an eddy occurs in this turbulent medium, and based on the eddy circulation time, if the Stokes number that you calculated from that is approximately 1, then you'll get preferential clumping. Well, in a statistical sense at the very least. And this is work that's done by Jeff Cuzzy and Thomas Hartlip and a whole number of people. There's some recent developments, and a paper is actually going to be coming out very soon in the next couple of months. Right now, the paper is just about to be submitted to APJ, led by Thomas Hartlip, which is a follow-up of his earlier study. So although I'd love to talk about that, if anyone's going to the Ringberg conference, I'll be there. So I'll talk more about this mechanism together with some other things over there. So what I want to talk about, of course, is the streaming instability. And this is our darling favorite mechanism to drive over densities in disks. And I'll say this right off the bat, I will not speak about the efficacy of the streaming instability in the outer solar system, only because it works, I think, and there's a time scale associated with that. But I would like to, there's some further work we're doing on that part of the story. So I can take some questions about that later. So I'm going to focus on the inner solar system picture. Okay, so the streaming instability. Everyone, the people who either invented this or have worked with this are probably all in the audience right now. So you'll excuse the conceit of giving a crash course, which is for those who are not familiar. The ingredients of the streaming instability is that you have a two-fluid system. One is pressureless, and then there's momentum exchange between via drag between the gas and the dust component. And here, the gas oscillations that are primarily responsible for what we see are in the form of inertial waves, inertial Coriolis oscillations because of inertial Coriolis effects. The original work, of course, Uden and Goodman, 2005, as applied to protoplanetary disks, goes without saying. One of the important components of all this, of course, is that there's a relative flow between dust and gas must exist in the mean state. Inertial oscillation timescales for this mechanism to be effective must be on the same, the inertial oscillation timescales must equal the momentum exchange timescales, i.e. the dust toppings times should be about 1 to be most effective. Local analysis, that's what was done in the original paper, and this is a very challenging problem when you add other effects into the mix, but nonetheless, the original story as applied to protoplanetary disk was done with the local analysis, and that the perturbations were axisymmetric. So there are several input quantities to keep in mind. There's the disk opening angle, there's the disk scale height. Disk opening angle here is delta. Disk scale height is h. The Stokes number here, I've defined it, is given by tau s, and the gas to dust mass density ratio is epsilon. On the right here, you see what are basically the Nakagawa solutions for the relative for the steady state velocities between the gas and the dust. And I won't go into that too much detail. Of course, if y'all, the last year or so has seen a very important advance in our understanding of what I'm going to term the resonant drag instabilities, work that was done by Squire and Hopkins. I was very happy to see this study. It really puts things into a very clear context as far as interpreting the streaming instability in this larger context of a whole range of processes. And the main point is that, and the insight is the following: because you have a drift between the gas and the dust, and they predict that instability is to be a very generic feature wherever some gas oscillation mode or some collective mode in the medium matches the drift velocities of the dusty component, or the relative drift velocities between the dust and the gas. So that's basically what's encapsulated in this expression down below here. I'll return to this in a moment. Let's talk a little about the streaming stability in laminar protoplanetary disks. Linear theory of Uden and Goodman show that that this effective scales are on the order of delta times h, so it's very small. That's presumed. That's if you are and of course, this is all driven by the fact that in the basic state there is a large scale pressure gradient which drives the the dust to gas relative velocities to appear in the first place because of a mean drag, aerodynamic drag that's experienced by the dust component. But nevertheless, the scales in which this happens is about delta times the scale height, so it's very small. What I call the choices parameter range is regime is between epsilon 0.1 and a little bit greater than 0.1, and Stokes numbers between 0.1 and 3. And the growth rates are on the order of orbit times. The growth rates are very profound. They can go very high in the laminar case. And when you add self-gravity into the mix, you could trigger overdensities that can trigger gravitational collapse. Of course, if the protoplanetary disk in the so-called dead zone or the ohmic zone, depending on how you want to term the process, are in fact weakly turbulent with an alpha given with some sort of given alpha, then we might have to reconsider whether or not this mechanism is going to be operative under turbulent conditions. When the turbulence goes away, i.e., when, for instance, because of photoevaporation, the disk evaporates, then the turbulence will either vanish and or the Stokes numbers go up, and then this mechanism is going to be quite active. But until then, I want to show you what happens based on some linear theory calculations. So we know that the streaming instability in turbulent protoplanetary disks has been looked at a handful of people. It started with Johansson et al., the great paper from Nature in 2007. Balsara et al. In 2009 followed up with that. And then it turns out that Fromming and Papalouzeau in 2006, I call it a pre-covery. They actually kind of had it in there, but they weren't thinking about the streaming instability in the way that we were kind of thinking about today. When you read the paper, you can kind of see that something is sort of happening there, but they were looking at how this process develops in a turbulent, MRI-driven turbulence. In fact, all of these, I think, if I remember correctly, this is all MRI-driven turbulence with alphas about 10 to the minus 3. So in these simulations, they all consider very strong turbulence, Stokes numbers on the order of 1/4 to 1, and order 1 dust to gas ratios. In these cases, as you see on the left here, you can see that there is overdensity of drives, and as we like to say, Bob's your uncle. So now let's get to the details of what we did. So what we decided to do was let's go back to the original analytic theory and let's put in a model for turbulence, just the simple-minded alpha disk prescription for momentum exchange and for momentum dissipation in the gas component. So that's what we do here. We have some velocity dissipation term here on the top line. And then we added in a term in the density equation, the mass density equation for the dust component, representing particle stirring, and it's given by this expression. Then we repeated the same analysis. First step, we verified that in fact we were recovering some of the old results, the original results, and indeed we do. What I plotted here is an example of the growth rates. Here, what I've done is done a scan in horizontal wave numbers, the x direction and the z direction. X is the radial, z is the vertical, and the color coding here is the growth rates. And the dashed line here is the resonance condition of Squire and Hopkins, which is very nice because it tells you that this very approximate sort of, I don't know how you call this, it would be like a sort of a guess condition, you know, to find the conditions in which this is most effective. This line here is the line that runs right down the middle of where the streaming stability is most effective. In other words, this line here is where the resonance occurs between an inertial wave and the drift velocity, and that's kind of given by this expression up over here. So this is very nice and very satisfying for me, and because I like thinking about things in these terms. So what do we find? So some general trends first. As you might imagine, when turbulence is high, the growth rates diminish. It's pushing down the areas in wave number. Obviously, if you go to high wave number, the dissipation is wiping out any structures that are appearing. So you see here a trend in which, in this top panel here, I guess my face is covering up my graph here because of the way the thing is looking. So, but I guess you could see behind, right over here, the growth rates get quite high. And this is in the relatively low turbulence case, but as the turbulence is increased, as in this particular case here, you can see the alpha here is 2 times 10 to the minus 3. The region of maximal growth has pushed all the way down to scales that are on the order of the local scale height. So that's the two main things you get, that the length scale, preferred length scales of growth go from delta times h to h. Growth rates also diminish. I looked at, and to see if there was any value in this sort of construction, I went back and I looked at what Johansson et al.'s 2007 simulation showed. And I'm going to, forgive me if I go over this too quickly because I want to get to the other results, but there seems to be a reasonable connection between what is observed in Johansson's simulations, Johansson et al. Simulations. In other words, what I did was I took what happened in the linear growth phase of their simulations and I compared the wavelengths of the mode to appear, the pattern speed of the wavelength that I saw, the pattern speed of the developing instability, and the E-fold and growth time scales. So that's kind of, I took, I kind of did some approximate measurements for what I saw in the graphs there. And in our theory for those conditions, we found that there was some reasonable coincidence between the two. So telling us that this is not totally wrong for obvious reasons. It might still be totally wrong, but not for this reason at the very least. So that gave us hope that there's something to go here. So this graph is the star of the show. If I don't get to anything else, I want to just simply talk about what's going on here. We did a parameter sweep across Stokes number and turbulence, values of alpha. On the x-axis is the Stokes number, on the vertical axis is the turbulence, is the alpha. And what we did was we scanned and we hunted down the maximally growing wave mode under those conditions. Now for when you do this, the linear stability analysis, there are actually 6 modes present, two inertial, well, more like 4 inertial, mixed inertial gravity modes. And then there are 2 zero temperature acoustic waves, if you want to look at it in those terms. But nonetheless, it's generally one. Sometimes there's 2 modes, but it's generally just one. And so I look here, I'm plotting here the dominant modes. And what we did was we chose the constraints to be the following. If the disk is turbulent, it's probably kicking up the dust particles. So we assumed that the Stokes number of the particle is a given, alpha is given, and then we chose epsilon, the dust to gas mass density ratio, to be consistent with the tendency for dust to settle against turbulence to kick the dust up. And so there are several formulae that have been developed by people like de Broglie and Estrada and Carballido et al. And this is essentially the sort of the formula that we use. Very strong turbulence. Epsilon should just be F, which is the global dust to gas ratio. When alpha goes to 0, of course, all the dust will settle down to the midplane. That's the kind of the picture here. What I have plotted here as well, as you can see, is these empty circles. The circles here, these are the plots of the previous streaming instability calculations that have been done. And the filled circles are places where the streaming instability is observed under the conditions. And the open circles are the ones in which there is no observed streaming instability for that particular numerical simulation. And it looks like, at least again, we're not totally off the mark here. So that's something to consider. But let's talk about the main deal here. There is a special line that in the alpha tau space, and it corresponds to values where epsilon is equal to 1 And when you're on that side of it, in other words, all models that are on this side of this line are values of epsilon that are less than 1. All values on this side are values of epsilon that are greater than 1. This line here sort of sets up a sort of a division of parameter space. And here appears to be what we're nominally calling a critical point. This division is pretty strong when you're on values of the Stokes number that are about less than 0.3. And when you're on this side, what I'm calling a turbulent regime, the growth rates are very long, very slow. However, when you drop down below this magical epsilon equals 1 line, everything changes very suddenly, and the growth rates become very, very strong, which is interesting to know. We don't yet fully understand the nature of this point here, why it appears, but we've checked it. I can't tell you the number of times we checked it, and it seems pretty robust. So let me get through some of the other things here. What I plotted here is essentially the same plot of the same model solutions that we've done. And what I plotted here is the pattern propagation speed. In the original paper by Uden and Goodman, it was identified that if your epsilon is less than 1, the pattern propagation speed, the phase velocity is inward and if things are flipped around, if epsilon is greater than 1, the phase velocity is outward. And so we see the same trend appearing here, but what we see up here in these strongly turbulent regimes, we see a strong, rapid inward phase velocity drift, which is very similar to what you see or in the original, in the simulations, for instance, of Johansen in 2007. So again, this is also quite fascinating. We're trying to make better sense of all this, but kind of give you a sense of what we have here. Okay, so I know of course, I always talk too much, so I'm going to give you the 3 minutes, and then I'll be done. What we did was we went through and we took this original, the growth rate plot, and we examined what parts of the phase of the parameter space are ruled out because of sort of physical properties happening, physical processes happening at, say, 5AU, the region of interest. So what I show here is the several growth barriers, which includes, in this case, the fragmentation barrier. So I show you here the regions in parameter space that are ruled out because silicates are destroyed because of the random velocities banging into each other. And then this line up here is where water ices, I call bite the DOS. You'll have to excuse my flippant use of language here. I include now on this upper side here, on the left side, you see what I call down the drain. It's the radial drift barrier. So basically what this is pointing out is that growth rates that are longer than the radial drift time, this part of parameter space is ruled out. And then this one may be controversial. This is the pattern drift barrier. If the pattern is drifting inward, and presumably the pattern is carrying the growing clump, as we see, for instance, in the simulations of Johansen, then if the pattern drift is faster than the e-folding growth time scale, we sort of said that this part of region parameter space is ruled out. So something to think about. This is open to debate, but that's currently what we're kind of kicking around in terms of how to interpret all of this. We label here what was the minimum, absolute minimum turbulence possible in the dead zone if you believe that the dead zone is active to these 3 hydrodynamic turbulence mechanisms. This line here comes from the turbulence alpha calculated by Flock et al. In 2016, I believe it was, where he estimates a relatively low value of the turbulence, 5 times 10 to the minus 5, or 4 times 10 to the minus 5. So that's what this line is over here. And lastly, Phil Bernstein and Paul Estrada have done a whole series of particle growth models in the global disks. And they show that while they looked at the problems, especially Paul looked at these models for a range of of disk alphas, and they routinely show that particles do not get past Stokes numbers of 0.01 as long as turbulence is active, while turbulence is active at these various levels. The simulations that have been looked at by Paul in their 1+1 global disk simulations do not have not looked at values of alpha down below. So this curve might dip below 10 to the minus 4 and arc out towards higher Stokes numbers when you drop down in alpha, but that is yet to be seen. So for this model at 5 AU, this is probably the region in which the streaming instability is viable. Now, there are problems here as well, but I have gone over time and I see people waving and I'm sure eyes are rolling in the back of people's skulls right now. So I hope I haven't done that. But so I'll stop here and I can take more questions at your will.
Thank you very much for a fascinating talk. Questions? Shuning?
Very interesting talk. So, you're considering streaming instability in external turbulence, but streaming instability itself produces turbulence. And would you think this can be a way to understand the nonlinear behavior of the streaming instability?
I think so. I think there will be some value in approach taking this to look at that, though I haven't. Let's go back to the original plot here.
If you also gather the data from just pure streaming instability simulations and get their alpha into this plot.
Yeah, so that would, and I think what happens, I think if I remember correctly, I have to look at them again, but I think, this is a good idea, and I can drop those down here, because I think the values of alpha in those simulations vary between 10 to the minus 6 and 10 to the minus 5. Am I right? I can't remember.
I think can be higher, right?
That's about right.
Says Vlad. Maybe. Yeah.
So those would plop down right around in this region here. So that might explain how it saturates, and that's a good point. And I haven't done that yet. I need to hunt through the lit. But thank you for the suggestion.
Okay.
Phil?
So once you've added turbulence into the mixture, there obviously could be there is a well-defined equilibrium stratified background state. So I guess I wonder, do you have any feeling of, okay, if you had that stratified background, would the linear theory be completely different again, or is there an argument to say that we're still good?
Yeah. Okay. If I had an hour, of course, I'd probably murder you all in the process. I could tell you a little bit about that. Yeah. So if it's stratified, then when you are asking the question about what's the maximum growing wave number, you have to also probably cut off the values in which the vertical wave number of this theory exceeds the stratified scale, right? I would imagine that's in other words, there's a natural vertical wavelength, and modes in this theory don't get expressed in a place like that because that length scale is sort of fixed. And that's not directly answering your question, but the answer is yes, and that has to be kind of considered with a little more nuance. That's not in here, but that would affect things absolutely. The closest thing I can say, of course, is that if you take, the particles are being distributed and pushed up from the disk midplane using this very simplified model that you can see here on the left here, where I constrain epsilon by the formula there. But if I understand you correctly, then you have to sort of consider that there's a natural vertical length scale that needs to be considered when making this analysis, and I agree, if that's what you're saying.
Jeremy?
I thought you were going to tell us. But
Turn on your mic.
triangle where you do get instability, it's expressed in terms of dimensionless parameters, but does that correspond to the size of these inclusions that you find in meteorites?
Right. So, of course, let's talk about that.
Was that by design?
Yeah. So the epsilon, so I did neglect to mention this. When you look at, let me jump over here, these simulations, well, rather the particle growth models, when tau is 0.01 in this area of the disk, that corresponds to particle sizes that are on the order of about a centimeter. So there seems to be some correlation between the two. But, of course, this is meaningless once the disk starts to dissipate and then the Stokes numbers start to go up. So while this is being active, this is probably the case, but let's say the disks were dissipating but the turbulence were staying fixed, then what would happen is if you were sitting over here, you would start drifting further in this direction in parameter space because your Stokes numbers start to approach 1, and then streaming instability takes over, and you're good. So this is so this model and this analysis is assuming that we are looking at what happens before the evaporation phase kicks in. I hope that answers your question and embellishes it a little bit too.
Okay, one last question.
I don't think that the evaporating disk calculation will work because as you remove gas, Stokes numbers will go up, so particles will collide faster, and they will fragment back down to the original Stokes number that I had initially. So you don't actually increase Stokes numbers by removing gas. Exactly.
Right.
So you're fragmenting them back down to the lower
Yes,
Stokes
of
number.
course. Yeah. So you're bouncing against this or this, depending on where you are. Let's say it's the silicates. You're just hitting this wall, you're saying. It's a possibility, yeah. But if the turbulence then starts to go down, and then you might be able to sneak past around it. But yeah, that's a good point. And that was my mistake. You're right.
Good talk.
Okay, thanks again.
Thanks. Hey, sorry I'm not there.